好想去看。
昨天去了吗？昨天去了吗？
去那干嘛？我这会儿
你干嘛？
要是跑出去，结果那个一片衣服让人打击。
可能老师也陪你，才练嘛，也陪你。
没有注意好，看你明天今天晚上。
不会讲。
Okay, let's get started. So anybody have any questions? Anything, homework? Statistics, of course. I've got maybe 20 minutes lecture to finish up some regroup things that are important to homework. And then Amon's going to take it from there. The next topic. Okay, so there's no questions. I'll jump right into it. The one thing we haven't talked about in the group stuff is group actions. We are going to be speaking specifically of Lie group actions. Although you can define group actions for more general groups, they don't have to be. Remember, Lie groups means it's a manifold and a group. You can have discrete groups that are acting on spaces and so forth and so on. But we're specifically, for the purposes of our geometry of data, manifolds, and such, we're going to be speaking about Lie groups, continuous or smooth groups acting on manifolds specifically. So a Lie group action is you've got you're given a Lie group G and a smooth, let me say smooth manifold. You clear a smooth manifold that it's going to act on M. That's the setup. A group action or a smooth group action is what we should really say. Smooth group action is a mapping and I'll write it in the following way. I take a group element, a point in my group, my Lie group. I take a point P in my manifold, and it maps to something I'm going to write as G dot P. There's lots of different notations for this, but this is an element in the Lie group across the manifold, meaning the order pair of 1 point from the group, 1 point from the manifold, and this output is going to be an element in your manifold. And the way to think of it is G is performing some type of transformation to map the point P to some other point on the manifold. That's all we're doing here. Okay. And but it's a mapping that is set up this way is this form, and it has this, as our usual definitions, we've got to put some rules or axioms down that this has to satisfy for it to be a group action. Number one is the identity element. If G equals E, then it shouldn't move the point P for any point P. So in other words, the identity acting on any point just returns that point back. This is for all points on our manifold. Okay, so the identity group element is like the identity transformation on the manifold. The second rule, not the most important one, is if I compose two G's, then I can either compose them first in the group, or I can apply them successively two in a row on P, and I'll get the same answer. So what we're saying there, if I take two elements GH, G concatenate H, that means multiply them in the group operation, GH, and I apply that to a point, it should be equivalent to first applying H to the point, and then applying G to that result. Okay. Looks kind of like associativity of group multiplication in a sense, but the second thing you're doing is not a group multiplication, it's the group action on the manifold P. Okay, any questions? I'm sorry, I should say for all GH in my group and all points P on the manifold, this property should hold. Okay, any questions about the rules? And this, we say we have a smooth group action, the Lie group on a manifold M. Okay, and this group action business is really the main point of Lie groups for purposes of this class, and really their main application is Lie groups in and of themselves can be interesting sometimes, but most often they're interesting, as we talked about, as transformations of things like geometry or data, where we talked about rotations and translations and scaling. We think of these as transformations of geometry or transformations of images. This is how to formalize that type of transformation in the mathematics of Lie groups. And obviously it's much more general than just those examples. There's lots of other examples of Lie groups and acting on general manifolds, but that's kind of why they're important. Okay, so let me do some examples, unless there's a quick question on that. Yeah, really quickly, we can take a group G being D-dimensional Euclidean space. We've seen that one, and the group operation is addition of vectors. And remember, we can think of this as D-dimensional translations of things. You can act on the manifold of the same thing, just positions in RD. Okay. And there I just take a point, the group action. So G got P. So G now is a vector thought of as the group, as the translation group. P is a point in D-dimensional Euclidean space. And we do just what you would think. I take this position and I get a new position by just adding this translation G to it. Okay. It's kind of weird to call translations G, but that's, you just sticking with this notation. So like in R2, for instance, I have point P and I just move it to a point Q, let's say, which is equal to, if this vector is G, that Q is equal to P plus G, right? Okay, so that's the board do this. Okay, we've got this problem with the board again. I think if I get too close to the edges, I think I'm going to try to stay in the middle of the board, see how this works. Okay. So yeah, very simple example. Let me do one more quick example, trying to be somewhat quick here. We can take G equal to the rotation group. We're going to come back to this example here when we talk about what we're doing in the homework. Actually, these are two examples in the homework that you're doing. And I'm just going to do 2 dimensions, but I can put a D instead of 2 here, same kind of setup. Okay. And now a little G, right, is you can think as a rotation matrix, a 2x2 rotation matrix. Remember, this is the cosine sine 2x2 matrix that we've seen a couple times. And now G dot P is let me change the notation because it's just getting kind of weird. Let's say capital R is a rotation matrix, the 2x2 matrix. The group action, if P is a 2 vector, a column vector, is just RP, where this is matrix vector multiplication, as we're used to. Okay, you just take your position P as a vector in two vector, and you multiply by the 2 by 2 rotation matrix. That's our usual rotation action. Okay, so this is we're very familiar with these things, but they are Lie actions, and you can kind of check the rules here. Obviously, matrix vector multiplication, if I concatenate 2 rotations, applying to P in order, is the same thing as multiplying rotation matrices first and then applying the result to P. So that's the second rule there. And of course, the identity matrix does leave points fixed, so that also checks out, and so forth. The one you're going to need for homework, the group action, is on images. Now, images gets a little bit trickier. It's not too bad, but it's a little, let's take G equal to let's do SO2, and let's do the manifold is the space of images. This is you can write this as L2 functions on some domain, I'll call omega, real numbers. This just means square integrable functions. So omega is my image domain. Omega is like a box, if you or a square, if you will. And I'm defining an image as just a function from any point in the image to the real numbers, just the intensity value at that pixel. Okay. This, of course, is continuous, like a continuous image. We, of course, have like pixel images, so we're approximating this space that we're this manifold that we're acting on. And so if I have, I'm going to call it capital I. So yeah, so this, by the way, I can think of this as a function I, which takes coordinates, let's say UV coordinates in here, and outputs this in an intensity. So I'll use the letter I, and I won't give it 2 coordinates. I'll just give it 1 coordinate, which is a two vector position. So let's call it I of X. Important here. So my group, I'll keep using capital R's for elements in SO2. And how do I rotate an image? So if I have an image I of X here, and I want the rotated image, I'll call it I tilde of X. This is a tricky question. Anybody know how to rotate an image? I have a rotation matrix R, a 2 by 2 rotation matrix, and I have a 2 vector kind of input coordinate. I know a few in here are image processing, image analysis people might know the answer to this, but anybody know how you apply a rotation to an image? If I'm going to write down another image here in terms of I. Let me get a I of something. I'm going to do something to this coordinate. I've got a rotation matrix R. What am I going to do to this coordinate here? Okay.
Multiply the vector by the rotation
By the R with the rotation. So I'm getting that like that. Anybody want to say yay or nay to this?
That depends on how you write your coordinates. You have to sometimes transpose one of them, but
yeah. So yeah, so you're actually in the right. So actually what you need to do is you need to invert the transformation. This is a little bit tricky, but let's figure out why. So if I've got an image of a tree, okay, and I want to rotate it. So this is my I, and I want to rotate it to I tilde, which is the tree rotated, let's say 20 degrees counterclockwise. Okay, my R will take a point and rotate it 20 degrees counterclockwise. Notice what I need to do is say, evaluate at a point X in I of tilde. Okay, so let's say this is X. I'm somewhere in the top of the tree here. Now, if I apply R to it, I'm going to rotate my 20 degrees, and this is going to be Rx. But notice if I look up Rx in I'm going to be over here at the image. So notice what I need to do is I need to go R inverse back here, this is our inverse of x, and that is the spot I'm actually going to evaluate I. Evaluate I in the inverse direction. So to kind of put a finer point on it, when I look up a value here, I need to go backwards, the backwards transformation to look up the intensity in the image here. So forward transformation is not what I want to do. Okay, so same thing holds, by the way, for translation. If you want to translate, let's say translation by some two vector v, then you do the same kind of thing. You invert, and inverse of a translation is just negation. So you go x minus v to translate in the v direction. It's a little bit confusing. It seems backwards, but you apply the inverse transformation inside. This is a little bit trickier to check the group action, but it also is a group action. Because you have to just apply the inverse and be careful there. Okay. So this is the kind of thing you're going to do in the very last problem of the homework is, and now you don't have to implement this function yourself. You can use a library like Pillow or one of the, I don't know, PyTorch, maybe some library that does rotation translation images. So please feel free to rotate translation images through a library, because doing this, you have to interpolate, do all this other stuff. And so that's what you will most likely do, but just be careful. When you rotate translate, know that you're applying when you apply that the group action actually looks like this. Okay. One more thing to say on that front. Yeah, let me leave this up. The picture here, right, is I have my I want to write this. I have my group G. I have M. There's the identity element here. But what I'm going to do is I'm going to pick a G somewhere in my group, and it's going to take P and map it to P dot G. And that's going to happen for every point in the manifold. So it's like I take the manifold and I reorder where all the points are by applying this G. So every point in the manifold gets transformed by any G I picked. If I pick E, of course, the map, it just, everything stays put. And so one other last thing that you're going to do in the homework, is you're going to look at infinitesimal group action, which is the Lie algebra. And so the way to think of that is, again, I'll draw the here, and at the identity, remember we have the Lie algebra is the tangent space at the identity. And what I want to know is that if I were to just perturb my identity element by a vector in the Lie algebra, how is that going to change a point on my manifold? Okay, so now I have a point in my manifold. And so a perturbation here would lead to a perturbation here. And the idea is that's the derivative mapping of this group action. Derivative really in the group element. The P can stay fixed, and I'm just want to know if I perturb the group element, what's the resulting perturbation, which should be a tangent vector here at P. Okay. The space of images is just a vector space. So the tangent space to an image is just an image. The tangent vector to an image is just an image. But it's the perturbation of the pixel intensities that are happening when you apply this infinitesimal group action. So in the homework where it says, look at the tangent vectors under the group action of rotation translation, you're going to see images. Those are the tangent vectors. And so how do you do that? Just computationally, we can think of this as the one parameter subgroup. So the curve passing through the identity with this velocity x. Okay. And that one parameter subgroup is exponential, the Lie group exponential, t times x. So this is like a curve gamma of t. Okay, and that curve is in group, so we can act on p. So I can take gamma of t and take that result and act on p. So I'm transforming the point p. When I do that, this is still a function of t. I'm getting a curve up here on the manifold. Looks like a continuous change in my manifold point. So you think of it's the image rotating continuously. If I move along this curve, for instance, it is the rotation action on the image. Okay. And what we can do is then say the action, the perturbation, infinitesimal action is just the derivative of this curve with respect to t, evaluated at t equals 0. Okay. And that's what you're going to do. Of course, in images, and you can't really take a derivative. Okay, you have to approximate this derivative. This is what I'm trying to say. So this is approximately going to be equal to the usual thing is I should say t plus epsilon, but I'm going to evaluate 0. So I'm going to say gamma of epsilon minus, applied to p, because p is going to be in a vector space. This only works for images or things that p's are vectors, because I'm going to subtract now gamma of 0 applied to p divided by epsilon. So you can pick a stupid camera. Oop. Sorry, I'm going to try to maybe I either have to stay in the middle or on the side. I'm not sure. Anyway, pick some small rotation, for example, for just the rotation example. Same thing with translations. This is saying generate a small gamma epsilon is a small rotation matrix. Rotate your image. Subtract gamma of 0 is the identity. So that's really just the same thing as p, right? So that's rotate your image some small amount, subtract the original image, the unrotated image from it, divide by the epsilon that you rotated by. That gives you an approximation to the infinitesimal rotation action. And again, that's a tangent vector in the space of images. That's what you're going to plot and see what that looks like. And you're also going to test if the autoencoder has captured image rotation. So if we have an autoencoder that's supposed to be capturing this data manifold that our images lie in, the question is the autoencoder manifold that it's learned, does it contain rotation? So if you rotated the image, would you still be in the manifold the autoencoder has learned? That's kind of the goal here. Okay. And a little bit of the detail on how you do that. Any questions? Okay, I've taken 3 more minutes than I was trying to take, and now I want to take 2 more minutes. That's okay. Because I did want to give a little bit more, because like I said, it's my favorite application of Lie groups and algebras is the parallel parking. So I did want to give a little bit more detail to guide you through that set of notes for the parallel parking example. And I think I only need a couple minutes maybe to do it, because I'm not going to go through all the equations and derivations. It's a lot of cranking through algebra. So one thing I want to say about the Lie bracket, to give you a better intuition of what's going on with the Lie bracket. Remember, we had this way to multiply 2 tangent vectors, 2 Lie algebra vectors together called the Lie bracket. And for matrices, I'll just say for matrices, this looks like xy minus yx. So like if we were an SOD or GLD, any matrix group, these tangent vectors are matrices, and the Lie bracket looks like this: xy minus yx. Okay. Now, if I again want a group at the identity, and I have x and I have a vector y, one way to think of what the Lie bracket is doing is the Lie bracket can be thought of as, again, we had this, remember, this derivative of commuters, G, H, G inverse. And what that, one way to write that, this commutation is there's one parameter subgroup. So I'm going to write a derivative of two parameters here, t and s, and I can write exponential of fx ey, and then the reverse minus sx. Sorry, I'm running out of room. Minus ty. Okay. So what's going on here? I'm saying take the one parameter subgroup forward along x. In fact, I shouldn't draw the backwards part. So I go forward. And let's go from right to left. It doesn't matter. I go forward along x, then I go forward along y. And y has to be thought of as this left invariant kind of vector, because I'm going to move it here. Then I go backwards along x. So thinking of where the x vector field is here, I go backwards here, and then I go backwards along the y. And so I go back this way. Now, do I get back to where I started? Oh, yeah, sorry. This is derivative t, derivative s, evaluate it at t equals 0 and s equals 0. Because I want to be at the identity at s and t equals 0. This is all at the identity because it's exponential of 0 everywhere. Okay, and so you do this, and you think about these one parameter subgroups. And of course, I'm taking derivatives, so this picture just would shrink down until infinitesimally. S and t are just infinitesimal in the limit. In the limit, does this point come back to the point I started at? And if it doesn't, there's some perturbation. That perturbation that you have left over, that is the Lie bracket. Okay. And this is, again, showing us how, again, as this in the limit, as a derivative, the group is failing to commute. So this direction and that direction aren't commuting, because if they commuted, then inverting the way you went would get you back to where you started, if this whole thing commuted. And this is how parallel parking works, because if you look again in the notes, there was that set of notes linked. Which is, by the way, it's from some book. You can actually look up the actual original book this example came from in the notes there. If you remember, we had this setup where I can turn the wheel and I can drive forward and back. Okay, those are the controls I have. And if I think of the infinitesimal action of driving some epsilon forward backwards as one vector, and then I think of turning as another vector. It turns out that if you do the Lie bracket of driving and turning, I will give you the general sense here. What that means is you turn, you drive, you can do it it doesn't matter which way you do it. You can turn, drive backwards, turn at the negative, the exact opposite angle, and then drive forwards. So you do each direction back and forth, just like this. You turn, drive forwards, reverse turn, reverse drive. Okay, something like that. And you can reversely do that. That they call a wriggle in the notes. So it's kind of like he calls it like a derivative of drive, which just means the infinitesimal driving, bracket with derivative of turn. That gives you this derivative of wriggle. I was going to draw it all here, but I want to not take all the time. But because the bottom line is wriggle, what that does is it takes you from this configuration, and there's your center, to just a rotated car about the center. And again, this only works infinitesimally. Of course, you can't actually rotate a car about its center directly. But if you take these epsilon drive, turn, reverse drive, reverse turn, you will, at least up to first order, just be rotating your car. And you're doing this again with, you just need epsilon space. That's why you can fit in any parking space with just epsilon. So that turns you, but that doesn't get you out of the space, right? You're still where your position needs to come out of the space parallel. And so the next thing you can do is another Lie bracket, derivative of wriggle with, again, derivative of drive. And this gives you something he calls slide. And it's called slide because if you do this turn, drive, forward, In fact, this will be a little bit easier to see. Drive forward. I've moved the position here. I now reverse wriggle, which gives me just a rotation here, and now reverse drive. If this makes sense, hopefully. You see what I've done is I've just slid parallel to my axis of the car. So this is why you can infinitesimally just slide out of a parallel parking space. It's just epsilon movements. You can essentially, again, up the first order, you're moving literally parallel to the curb, or perpendicular to the curb, I guess, but parallel to the out of the parking space. Okay, so if you're interested in kind of the nitty-gritty actually computations of these Lie algebras and those things, you can, and it is also a group action, by the way. So the group, you don't even specify what the group is, but the group is just generated by drive and turn. Those are the only two operations you need. And notice the dimensionality, you've got 2 degrees of freedom, drive, turn, it's only 2 dimensions, but because they don't commute, you actually have more dimensions that happen. So it's like you have an X and a Y, you take the bracket, you get a third dimension that you didn't have before, which is the wriggle dimension. And then you get another dimension, which is the slide dimension. And if you take all of those dimensions together, they span actually 3-dimensional action, because you only have 2 degrees of freedom here, and the orientation is 3 of the 3rd degree of freedom. So you're actually taking 2 controls and manipulating a 3-dimensional space. And it only works because the Lie bracket doesn't commute. Okay, so yeah, the details are, if you really want to be clear on what's happening, the details are fun to go through, but that's the idea. Okay, I'll stop now. That took 30 minutes. Any questions? Okay.
Two of us up here, we'll see which one. Track is here.
I think we'll move forward. So the light is red on this.
Here, let's see if it makes, because sometimes the red. It's the word. It usually means it still hasn't used the because it was green when I started.
Okay. Okay, so we will now sort of study another type of generative models. We've seen variation autoencoders in the recorded lecture, and we saw a little bit of neural networks. So this part of class now, in the second half, we'll see a little bit more applications of manifold related math, and specifically in deep learning. So we'll cover different types of models in latest AI literature, and see how all of them sort of connect to the manifold math and the manifold related stuff that we've been learning. So today we'll specifically look at normalizing flows or flow-based models, and different types of flow-based models, and also like what is the fundamental math behind flow-based models. And then you can sort of look at it a little bit more in detail in your own time and see what are they used for, and how you can use it maybe for your projects or something like that. Okay, so we're doing flow based generative models. Okay, so before we start looking at what flow-based models mean, let's just sort of review what we understand as a generative model. Like, what do we want from a generative model? What is a generative model, right? Does anyone have any intuition? Like, what would be a good property of a generative model?
A generative model should be able to learn the underlying basic characteristics of the data, so that it can generate more data,
Correct.
which looks like real data, but it's actually fake.
Yeah, that makes sense. So essentially, a generative model is trying to learn the real data distribution, you sort of try to fit a distribution on the real world's data distribution such that you are able to sample from it also. So it is very important that if you train a generative model, it should be very easy to sort of sample from that model, which is what we are interested in. We wanted to sort of generate more data, which is not really in the training data set or does not belong to the training set that you use, but look close enough to the real data so that follows the same distribution. But we are able to sample an infinitely many number of samples from this distribution, right? So that is what we want from a generative model. So let's just set up the problem first. Let's say we have a data set of n samples. Right, and each of these is d-dimensional. So we have d-dimensional data points, and n of those. So what we want is that we want to learn a model which is p theta of x, is the probabilistic model that we want to learn from this data. What this model should be able to do is that given, let's say, a latent code z, which is sampled from a normal distribution, and we use this as a normal distribution with the easiest to sample from, but what we want is that this z should be sampled from a distribution that is known to us, so that we can sample an infinitely many number of z's from this and then sort of generate data using these g's that we sample. So this latent code should follow a distribution that we know. So let's say that's a normal distribution, and x is the data that we want to sample using like a function g theta given the values, right? So we want to be able to sample from this probabilistic model in two steps. The first step is that we get a z from a known distribution. You randomly just sample a value of a latent code. Then you use a function which takes in the z and gives you a new data point x, right? We also want that this g of theta should be a bijective function, and also an invertible function, which means that for each point in the dataset x1, it should map to a unique point z1, and if you sort of decode that point z1, it should go back to x, right? It should be a bijective mapping between the latent code and the real data distribution. Okay, so this is the setup that we want from this generative model, and there are two processes in this. The first one is the generation process, where you are going from z to x using the function d theta, right? This is the generative process that we're talking about. And the reverse process is when you go from x to z, right? And this is what we call as the inference process, because inference or encoding or something like that, because what you're doing is that you're taking like the real data point and encoding it as a latent code. Also note that we're using the data as a d-dimensional vector, like the data is d-dimensional. We also sort of assume that in this setup, z is also d-dimensional, right? So the latent code is actually the same size as the data. So you're not really compressing anything, you're just trying to come up with a representation of that sample in a more structured way so that you can recreate more samples like that. Right. Another assumption that we are making here is that this g theta, the inverse of this g theta function is this g theta inverse. Like I'll just say this is g theta inverse. And for the sake of simplicity, let's just call this f theta, right? So f theta is just the inverse of g theta. So these are both, because this is an invertible function, there are two functions that exist, one in the forward direction, one in the backward direction. And these two are like sort of inverses of each other. The assumption here, one assumption that we are taking is that f and g are differentiable function. And why do we want these to be differentiable functions? Is that because we'll be optimizing these models, these parameters theta, using stochastic gradient descent. And to do that via like a gradient based algorithm, you want the functions to be differentiable so that you can calculate the gradients and be able to sort of change the parameters and tune the parameters using those gradients. Okay, so this is the overall setup that we want. And now we look at what are the problems in optimizing a setup like this, and what are the mathematical workarounds that we'll have to come up with. But before that, let's look at one example, just a very simple example of this in one-dimensional space where d equal to 1, so that we can see what the math looks like in that case. Okay. So for this example, we are assuming that d equals 1. And because d equals 1, we can just plot a function between our value c, the latent code, and x, which is the data. Both are same dimension. And we have this function g of theta like this, right? And this is an invertible bijective function. Okay. Okay, so now assume that you have a density in Z space, because we know what the distribution is here, right? We know what PZ is because that's a latent code distribution and we know what it is. So if we sort of come up with the interval here and we want to sort of capture the distribution that this captures, we know that the probability of sampling a Z, which is in this range, is P of Z times TZ, right? That makes sense. Okay. And the image of this same interval on the x-axis through this function. And this follows from a very common sort of rule, which sort of says that the probability mass should always be conserved in situations like these. So to have the probability mass be conserved, this we know is px. We don't know what px is, but this would be px times dx, whatever px times dx is. And based on the conservation of probability mass, because probability mass is conserved, you have P z dz equal to px dx, right? That makes sense. It's just a rule. So because the probability mass is conserved across this function, you know that this interval would be equal to that interval, right? And here we know what pz is, and what we are interested in is just px, which is the distribution of the real data. We just put that on one side and write it as pz times dz by dx. Okay. And this is called the change of variables step. Okay. So this is for d equal to 1. So for d equal to 1, this math sort of very simply comes to be this. And what this essentially sort of intuitively means is that how much does the small interval in z change with a small change in the interval of x, given these two probability distributions of those variables, right? But this is only applicable for d equal to 1. Okay, when the dimensionality is 1, this sort of works out. But for higher dimensional spaces, how do we generalize this? Okay, so let's look at the same thing in d greater than 1, like in higher dimensional spaces. So the math is a little bit more complicated, but because we understand the intuition based on this one-dimensional case that we saw, we can just generalize this formula for higher dimensions without actually computing what it is. Okay, so we'll just use intuition to sort of generalize it to higher dimension, and that happens as well. So in higher dimensions, let's say where d is greater than 1. So here what will happen is that this length of intervals, the ratio of the length of change in the intervals will be replaced by the ratio of change in volumes. Like instead of this being measured as one-dimensional intervals, this ratio will now be measured as the change in ratio of volumes as higher dimension spaces. This plot will be multiple dimensions, so it won't be just an interval change in interval anymore between these two sort of the latent code and the data. So what will happen is that this ratio will have to be expressed as a change in volumes, right? So that's the only thing that will change. The rest of the formula stays the same. So we can just sort of redo this for higher dimensions by just replacing this with the ratio of volumes. Okay. And now one more thing, which is very convenient for us, is that the ratio of volumes in higher dimension spaces is just determined by the determinant of the Jacobian matrix from Z to X. Okay, so this in higher dimensions just reduces to the determinant of dz by dx. Right, for d greater than. Okay, everything else is the same. It's just that we are representing this ratio as a ratio of volumes, which is just the determinant of the Jacobian of the transformation function between z and x. Okay, and the transformation function, I'm just sort of writing it as dz by dx, but this you can replace it, sort of represent it as j, which is a Jacobian, which is d cross d. Right? Because the d is the data dimension, it's a matrix, so it's a d cross d matrix that way. Right? And this is called the Jacobian. Okay. Now let's just write this thing for higher dimension theory. So what we get is that P of x is equal to P of z determinant of dz dx. Right? This makes sense? Yeah.
Quick question,
Mhm.
which part of the determinant expression were you saying can be by the Jacobian?
Just this part. So this we'll represent as like the ratio of the volumes, and the ratio of the volumes for higher dimensions is just the determinant of the Jacobian, and this is the Jacobian, right? So determinant of the Jacobian, the whole thing sort of replaces this.
Okay, thank you.
Mhm. Yeah, so we just instead of this, we just write this whole thing, and this is just the Jacobian, which is d times d. Okay. Right. So now let's just expand this and write it in log terms. Okay, just to see what that looks like. So taking log on both sides, you get log p of x equals log p of z plus log of determinant j. Okay. Right, I've just replaced instead of this, I'm just writing j now. So we'll always now just write the Jacobian matrix because that's what we are concerned with to do this computation. Right. So now how do we? So this is the likelihood, right? This is the likelihood, the log likelihood of the data that we want to sort of optimize on. We want to maximize this value, but how do we solve this optimization problem? Is the next step. So we solve it using our favorite method of optimization, deep learning model. which is the maximum likelihood estimation. Okay, so maximum likelihood in this case would just be we maximize this value over the parameters theta for the data set. Recall that the data set is x1 up to, let me just write it again. The data is x1 to xn and xi is d dimension. Okay, so we maximize this likelihood over the data set. So summation is equal to 1 to n. And what we want to maximize is log p theta. Right? This is the maximum likelihood objective that we want to solve. Okay. Now, this is always a positive value, right? It's probability between 0 and 1. It's always a positive value. And the log of probability will always be a negative value then, right? So this is a negative value. And it's harder to optimize negative values. So we would rather have these values be positive. So instead of maximizing the likelihood, we minimize the negative log likelihood. Okay, and that's a standard thing that all of these optimization based problems do. So instead of maximizing this, we change this to minimize the negative. Same thing, just I equal to 1 to n and minus log of q theta xi, right? So this is the negative log likelihood that we're trying to optimize, and this is all measured in bits or a pure information metric like that, like bits or maybe nats. Yeah, so those metrics. Okay. Now let me just write this in the context of the model that we have designed, which is a flow-based model, which is directly sort of invertible, which is just made up of these determinants and invertible functions. So when we expand this for that specific case, what we get is that we're trying to minimize over theta. I'm taking the negative outside, so minus 1 by n. And I'm just replacing the value of p theta of xi from here to get this summation to n. Means that this is computed at the point xi. Okay, so this is the objective that we have to optimize to sort of train a model like this using stochastic gradient descent or anything else. Let me see if there's a question. Yeah.
Just to be sure, data corresponds to the iterator in the data set. So it's like, are we trying to maximize the probability, mean probability
Yes.
of the
Over the data set. Yes, so we are trying to maximize the likelihood over this data set. So for each value, we optimize these parameters so that the overall sum is the lowest. Or if you're maximizing it, then the overall sum should be highest. So yeah, so we're just sort of optimizing this over the entire data set to come up with a map that agrees well with the entire data set, and that sort of generalizes to unseen data as well.
Since we're minimizing that, what would just be a gradient over
In this case,
I mean, like, would be just a negative minus the gradient of the log PZ, right? And the other one is just now, right?
Yes, correct. So for each point xi, this value will keep changing, and this log pz will sort of be similar, but this also has the parameters theta in it. So that gives you gradients for optimizing the value theta. But this one will also be sort of have the parameters in it. We'll see in the next few steps of how this is exactly computed. Now, so what is the problem with this? We have like an optimization bound also. We have parameters theta, we have neural networks that sort of go in both directions, we have invertible functions. Now, what is the issue with optimizing this? The main issue, yeah.
No, I thought that was a question.
Oh, yeah, yeah. So yeah, let's make it a question. What do you think?
I mean, I may be wrong, but
Yeah,
it seems like it depends on dimensionality because we're going over each
Exactly.
point in the vector,
Correct.
and if you have like 100,000.
Yes. Yes, exactly. So because the size of the data set can be arbitrarily large, and this determinant itself is D cross D, right? So this is always like, even if you take 128 cross 128 dimensional images, this is already 128 cross 128. And then there's a large data set. So it's very expensive to optimize over this determinant. Like it's almost computationally intractable to do this directly for normal problems. And even if you are able to do it, it's not expressive enough to sort of capture the intricacies of the data distribution. So this is very expensive to calculate, is what is the problem here. Otherwise, this already should start working, but this is not very easy to compute. So the idea now, how do we solve this? There's no, easy solutions to this. So let's look at a few solutions that people tried, and then we'll eventually get to the one that actually works these days. Okay, so the first idea is to so the simplest idea is, let's call this idea number one. And it is that we come up with J, which means that you also have to come up with corresponding F from G functions, such that the determinant of J is easy to compute. Right? It's the simplest thing that you can sort of, what you want is that we come up with the function such that the determinant of the Jacobian is already very easy to compute, right? And how do we do that? We'll see that. So there's a trade-off between doing this and making the functions expressive enough. So the trade-off is between this versus we want F comma G to be highly expressive. Right? So the issue is that the easier you make the determinant, the less expressive these functions become. And the less expressive they are, the less capable they are at modeling the data distribution. And the more complex you make these functions, the harder the determinant is to calculate. That is a trade-off that we have to sort of deal with here and solve. So the first idea is just to, let's say, come up with like an invertible map, which is the easiest, but let's see how it's not expressive enough. So just as like an easy example, let's look at invertible affine transformation. Okay. So we are assuming that this forward and backward transformation from z to x and x to z is just an affine transformation, okay, and is invertible. Now x, because it's an affine transformation, is just a is b plus b, okay, which means that c is equals to a inverse of x minus b. Right? And the Jacobian here then simply is dz by dx, which is equal to A inverse. Right? dz by dx is just A inverse. From this equation we can see. So we chose the easiest, right? Because there's a trade-off between this. We chose the least expressive function that we know. It's just an affine transformation, right? But even for the easiest function that we could come up with, the calculating the determinant of this is already very expensive. You see what I'm trying to demonstrate here is that even if you choose the easiest invertible affine transformation as your function to go from z to x, and the inverse to go from x to z, even in that case, the Jacobian, the determinant of the Jacobian is very expensive to calculate, right? That is what we're trying to demonstrate, that there are no easy answers to this problem. Yeah.
Is the some kind of bias in this?
Yeah, it's just a bias, yeah, because we are transforming z sort of to x, and it's just an affine transformation. We just do like sort of like a rotation matrix and then a bias. Sorry, transformation matrix. Just weights and bias. So it's just one step. Like you can imagine it as a one node of a unit without any linearity.
Is something not given to us? Is the
Z is the latent code. So yeah, I rubbed it off, but in this generative model setup, Z is the latent code that you sample from a known distribution, and X is the data that we're trying to come up with. Okay. So here, even here, this is very, very expensive. So now we can see how difficult it is to solve this problem, because even an affine transformation is not invertible. So now idea number 2, is to design a Jacobian matrix such that the Jacobian matrix is a diagonal matrix, it only has diagonal elements. Right? So the first one didn't work. The second one is that we design J to be a diagonal matrix. Right? And why would that help? Does anyone see that? Why would have it? Yeah.
to compute?
Yes, because the determinant is very easy to compute, because now that you only have diagonal elements, it's just the summation of the product of all the diagonal values, and if you take the log of this, it's just a summation of the log values of the diagonal, right? So if you design J to be a diagonal matrix, then the computation of the determinant becomes very easy, right? So because here what will happen is that J will be J11, J DD, and 0 and 0. The determinant of J will just be equal to the product of there are two i's and both sort of code D and J and okay, and the log of the determinant, because that is what we care about, is just a summation of I equal to 1 D log. Right? So that solves the computation problem. But now we have to sort of see what kind of a transformation function, like what kind of an F or a G pair would give you a diagonal matrix also, right? Because we are sort of assuming we're going like sort of trying to solve this problem backwards by sort of first finding a J that works for us, and then trying to come up with like an F and G which sort of agrees with this J, like which gives you this J. Okay, so what kind of a transformation function? This is slightly hard. What kind of transformation function do you think would give?
Just to make sure the since we are placing I assume each element of the Jacobian matrix into the diagonal, right?
Correct.
When transformation essentially matrix multiplication.
Yes.
So we want to do, when we do row by column multiplication,
Yes,
we want all of the other terms to be zeros and the first term to be preserved
correct.
as we travel through. So
Yes.
there's definitely going to be a lot of zeros and one at some ones,
Yeah.
probably along. You just need to figure out where exactly those ones are located, but
Yeah. So for the non-diagonal elements to be zero, if you think about it, the Jacobian matrix is just the derivative of the first dimension in X divided by the first dimension in Z, right? So what we want is that only the dimensions that are aligned to have positive values, but everything else should be zero, which means that any other dimension in X should not depend on any other dimension in Y, right? Sorry, in Z. So the first dimension of Z should give you the first dimension of X, and the second dimension should give the second dimension of X. Like these should be independent element-wise transformations, and that way, because any of the outputs dimensions are not dependent on non-corresponding elements in the input, only the diagonal elements will be positive. Right, let me write it out. I think that'll be clearer. If we choose f of theta of x to be, let's say, just a collection of element-wise functions, right? So f1 is only acting on x1, and then f is only acting on x2. Dot dot dot. The same function is also independently acting on xd. Right. So if this is the type of function that you come up with, where it's only applied element-wise, like it's not taking any two dimensions into account at the same time to come up with the output. This is Z1, this is Z2, this is Z. So what you will see is that the dth dimension or the ith dimension of Z is only dependent on the ith dimension of X, which means that all of the non-diagonal elements will be zero in the Jacobian. That makes sense? Okay. Any questions? Any questions? Okay, but now again going back to this trade-off, like this works, if computationally works, but this is again not expressive enough. Why? Because it's only looking at one pixel at a time. Like imagine that you have images, X is an image, and it has like 128 dimensions. Each dimension in the output or the latent code is only sort of predicted by one pixel in the input. So it's not really looking at multiple pixels at the same time. So it's not very expressive at all. Like you would just sort of transforming each pixel to a different value and trying to see if that is able to capture the distribution or not. Which even intuitively you can see that it won't, because you have to sort of look at the whole image and see what is there in the image and sort of understand the relationship between different pixels of the image to be able to come up with a larger data distribution. So this again is not expressive enough. So we have to come up with something even better, right? So now we come to an idea which sort of works, and then the one after this will be the one that actually works. Okay. Right. So now people notice that for the Jacobian to be easily computable, it's not necessary that it only has diagonal elements. It would also work if it is a triangular matrix. So J is a right. So what we want is that J should be J11, J D D. D should be 0, but the elements over here can be non-zero. And even for this case, what happens is that the determinant is again, just the product of the diagonal elements. Right? And the log of the determinant is just the sum of the diagonal element. Okay, so again, we see that this is easy to compute, but is it expressive enough is the next question, right? So what kind of an f or a transformation function would give you a Jacobian like this is the question, right? Now we have to come up with transformation functions f and g that sort of give us a triangular Jacobian matrix. And this happens like this. It's a very interesting way to do this, and it's really nice that they came up with this. And if you want to learn more about, read up a little bit more, this all comes from a paper called Real NVP. Okay, so you can look at that paper for a little bit more detail. But what they came up with is this, right? So you split your input into two parts, x1 and x2, right? So let's say this is an image. You just randomly sort of split the image into two parts. The first part is just this, like the first half of the pixels of the image, and the second one is the second half of the pixels of the image. Okay, and then we define a function f so that we get the latent code, which is also sort of in two parts. We get z1 and z2. Okay, and what we do here is that we just set the transformation for the first half as an identity function, which means that z1 is directly equal to x1. Okay, so the first half is just an identity function. So what you do is that you just copy the values in the input as the same thing in the output, just an identity function. The second half, the lower half, is what we design as an affine transformation. Okay. The second half is what we define as a affine transformation, and the affine transformation is defined as such. So z2 is s theta times element-wise multiplication with x2, which is the second half of the input, plus a bias term t theta, right? And these two are sort of neural networks that take in x1 and then predict these t theta and s theta. Okay, this overall is an affine transformation, but these values themselves are sort of predicted using x1. Okay. Right. Let me just write that this is dependent on x1. And this is okay. So now with a setup with a function like this, how do we get a triangular matrix? Is what we should look at, right? So let's say this is the triangular matrix. The top left part, which is just dz1 divided by dx1, what would this be? Anyone? dz1 by dx1 for that function?
Yeah.
Correct. It will just be an identity matrix. Sorry, an identity, right? This is dz1 by dx2. What would this be? Yeah, correct. This is just 0 because z1 is not dependent on x2 at all, right? z1 is just dependent on x1, so directly 0. Now this is dz2 by dx1. What would this be? Yeah, so this is slightly like complex to calculate. So this I'll just write at dz2 by dx1. So this is the term that is actually present, it's not zero, because this is the bottom half of the matrix. This will not be zero, there will be some values here, but it won't matter what these values are, as we will see just right now. Okay, so I'll just write it at dz2 by dx1, whatever that is. Okay, and this is then just dz2 by dx2, which is the diagonal elements of SK2. Okay, that makes sense, because this is not dependent on x2, this will go away. This, the only thing that is dependent on x2 is this, and because it's an element wise a product, the only the diagonal elements count. Okay, so this is the Jacobian that you'll get. And now because there is a zero here, when you sort of see that like when you're trying to calculate the determinant of this Jacobian, these values will not matter at all anyway, because we only care about the diagonal elements. As we saw here, the determinant is just a product of the diagonal elements. So irrespective of what this is and how complex this transformation is, it wouldn't matter because this is zero, right? That makes sense. So now this kind of a setup is finally that is something that sort of works, right? Next class we'll see what are the problems with this, and then we'll look at one more method that is sort of what is used these days. All right, any questions? Thank you.